Hello guys, today I want to show you how you can prove that the derivative of x to the any fraction is going to be equal to the power rule, okay? You know what the power rule is. So basically what we're going to do today is we're going to show that the derivative of x to the m over n is equal to mn over mn minus 1, okay? And now, how are we going to do this? We're going to use implicit differentiation, okay? And kind of like logarithmic differentiation. You know, it's like a combination of both of them. So, yep, let's do it. It is pretty simple. As long as you know some logarithmic properties, you're going to be fine, okay? So, let's begin. Now, the first thing that we want to do is we want to define a new variable. So, we're going to let y be equal to x to the m over n, okay? Now, we're going to do the following. We're going to take the natural log on both sides. So we know that ln y is going to be equal to ln x of m over n. And remember, 2m over m. And remember that there is a property that tells us that if you have ln of x to the a, you can basically move a to the front and multiply a times, and do a times ln x. Okay, so this equation is true. This is a property of logarithms, and we can use it to move mn to the front. So we have m over n times natural log of x, okay? This is how much we get, and that equation is true. So now you know that in logarithmic and implicit differentiation, usually you take the log on both sides, and now you take the derivative. And that's exactly what we're going to do. So we're going to take the derivative of ln y and m over n times ln x, okay? Since they are an equation, you can basically forget about this middle, like this middle part. You can take the derivative on these two terms, okay? So we're going to have the following. We can say that the derivative with respect to x of ln y is going to be equal to the derivative with respect to x of m over n times ln x, okay? And now we just simply need to use implicit differentiation to solve for dy over dx. So let's do that. We know we're going to have first the derivative. I'm just going to show you the chain rule explicitly. So dy over d over dy of ln y times dy over dx, and this is going to be equal to, now we know that this derivative is going to be mn, or m over n, I'm sorry, times the derivative of ln x, we know is going to be 1 over x, so 1 over x, and now we just simply need to solve for dy over dx. So we know the derivative of ln y is going to be 1 over y times dy over dx, and this is going to be equal to m over n times 1 over x, okay? And now you know that you can just simply multiply y on this side, and let's see what we get. So we know we get dy over dx is going to be equal to y times m over n times 1 over x, okay? And now how much is y? Well, we can see that at the beginning we defined y to be equal to x to the m over n. So we can rewrite this. This would be the implicit solution, but now we want the explicit solution. So it's going to be x to the m over n times m over n times 1 over x, which I'm actually now going to write as x to the negative 1, okay? This is negative 1. And now you know that using a property of exponents, you can do something with this negative 1 and this m over n, okay? You know that if you multiply two numbers with the same base, you can add their exponents. So basically you're going to have, you can move this mn anywhere you want. I'm just going to put it first. So you have mn times x of m over n plus minus 1. That would just simply be minus 1, okay? And I think you can see now, well, the beautiful power rule that you already know. So you basically have m over n. I'm going to do it without the parentheses so it looks better. M over n minus 1, okay? This is how much you get. And this is basically the proof, or you know, the derivation of the power rule for fractions using implicit differentiation and a bit of, you know, logarithmic differentiation over here, okay? So yeah, that is pretty much everything. You can see that this is pretty simple. I just wanted to show you how you can prove that the power rule is true for fractions, okay? Because you know that it is true for integers, but well, what about fractions? You know that it's also true, but you know, just a little proof using something interesting like implicit differentiation. I think it is something cool, okay? It is something cool to do. So yeah, that has been everything. I hope you enjoyed this video, you learned something, and see you in the following one. Bye.